Well, hello everyone, and welcome to this session of Oracle Machine Learning Office Hours. Today's topic is Machine Learning 101 Regression with Marcos Aranzubia, and my name is Mark Hornick, Senior Director of Product Management for Oracle Machine Learning. For Machine Learning 101 Regression, we're going to learn how to set up data set for regression modeling, build machine learning models that predict numeric values, such as home prices, evaluate model quality, and compare algorithms, as well as using AutoML for regression. In today's session, next we're going to talk about the upcoming session. Then Marcos will take us through Machine Learning Regression 101, and then we'll follow up with some Q&A. If you have any questions you'd like to ask during the session, please don't hesitate to use the Q&A option there or the chat. The next session is targeted for August 4th, and that's going to be Machine Learning 102 Regression. So we're going to take our discussion today to the next level and share a few more details about how do you work with regression models in more detail. If you'd like more information on Oracle Machine Learning, go to oracle.com/machine-learning, and you'll get a lot of resources as far as the various components to the Oracle Machine Learning product family. And if you're interested in taking a test drive of the autonomous database, you can access the always free services by this URL, oracle.com/cloud/free, and you'll be able to create PDBs, databases, and start working with the OML notebooks. So without further ado, I'll turn it over to Marcos. Marcos, welcome, and thank you very much for this session on Machine Learning 101 Regression.
Thank you very much, Mark. So thank you for joining. I'm Marcos Aranzubia. As Mark mentioned, we're going to be talking today about Regression 101. Just to have an idea of what it takes, right, to build these regression models and even use AutoML with it, right? So I will skip the part where we talked about what is machine learning, right? That's the first lesson of this course that we have been doing. So you can go back 3 sessions. We had an introduction to machine learning. So we're going to go into what is regression, a little bit of the history of it, the types of data needed, terminology, on data preparation, a little bit of intuition as well, and some mention about linear regression and other types of algorithms used for that. And finally, we will talk about model evaluation and AutoML. So the regression itself, right? Normally, the regression modeling can be applied to many different types of business problems. A little bit differently than classification, where we were trying to predict an outcome of good and bad or 0 or 1. In terms of regression, we're trying to predict a continuous valued outcome. So something like a credit scoring or a credit limit, right, where you have many values, right, that a number can take based on income, on past behavior, past payments from customers, credit limits, things like that. The same thing happens with future stock prices, right? Those are variable numbers, right? It's not just good and bad. Things like a value of a house, right? Based on the location of the house, number of rooms, lot size. There are things like neighborhood crime levels, right? And schools and other things that can be considered. And finally, one of the most classical ones that's been, something that people have been playing for a while is as trying to estimate the arrival delay of a flight based on the departure delay, based on the carrier, based on the day of the week and the day of the month and the origin and destination of the flight and other metrics, right, that you can find. So again, those are all values that are continuous, right? So in general, then, you start with the regression by identifying the values that are known, right? So you're looking at the past, again, taking the data that you know and identifying that value, right, that you want to estimate. And then during the model building, right, is when the regression is going to estimate the value of the target as a function of the predictors, right? And then that relationship is going to be summarized in the model. So there are many computing various statistics, right, that are computed during the build of a model. and especially measuring the difference between the predicted value and the expected value. So we're going to basically look at that and look at, of course, dividing into training and test data sets and understanding what the regression does with that, right? But a little bit on the history of regression, and I think this is very unique and interesting as well, because what happened was basically Francis Galton, right, which is actually the cousin of Charles Darwin. Back in the day, he was doing some basic analysis, and he was thinking about peas and the size of the peas. And what he did is he was trying to say, okay, if the peas have the parents, right, of the peas, of the trees, right, if the parents are all big, right, so I get my largest peas and I give it to some friends, and I get the smallest peas and I give it to different types of friends, and now I want to see what happens to the daughters of those peas now, right? So what happened is, instead of getting only the larger getting larger and the smaller getting smaller, right, he noticed that there was no correlation actually between the size of the daughters and the parents, but there was a correlation between the size of the daughters and the grandparents. So what he called that was a regression to the mean. So the regression to the size of the average of your family. And actually, he noted that also happened to people. So he presented a paper specifically about that. He did a congressional address explaining that back in the day. So, and it was in the 19th century. So the idea here is that back then, the name regression basically was created because it meant that you would go back to or regress to the height or to the size of your family, right? So that was a very interesting twist. Now, a more modern approach, right? When you think about a regression being used on computers, was actually on these gigantic 7090 mainframes in early 60s, where they were trying to build a credit score model. But because of the memory, right, back then, they were only able to do that with 600 customers and 25 attributes. And that was already an incredible achievement, right, of the day. So being able to do that much compute, let's say, right, in that data set. So for us, what we want to take a look today in terms of examples is actually trying to play with the arrival delays of domestic flights, right? There is an on-time data set that is famous. It was shown at the American Statistical Association Data Expo of 2009. That data had at that time 123 million records. So it's still available. If you go into that link, you can actually download that data and play with it. But actually, the Bureau of Transportation Statistics keeps a tab on that data, and you can actually go there and download much more data, right? You can actually keep downloading the latest months of data to complete your data set, for example, and then you end up with more than 200 million records easily there. So that is a well-known data. So how do we go by trying to evaluate arrival delays, right, on domestic flights? So if you think about it, right, we saw this before with the classification. So what we're looking now is I have arrival delay on the right, and that is in minutes, right? So my flight arrived on time, I got 0 minutes. My flight was delayed 20 minutes, my flight was delayed 15 minutes. And then when you look at the other variables that are there, right, you might see the carrier, right? You might see the departure delay. You might see the origin of the flight and the destination, right? So at the end of the day, when the new data set comes in, right, the idea is that you split that data out and you get a new data set in that is your test data set now, and that new test data set is going to have the same variables, right, and the distance and all of those things, but now you want to have your model predict that arrival delay, right? So if one day you get a perfect model, that means that the second that the flight departs from any of those places, right, by knowing the carrier, the origin, the destination, the distance, right, you will be able to estimate, the delay of the flight immediately, right? So that'll be something great to have. So when we look at the terminology, right? The terminology for these components, right, is similar again to the classification case. The difference now is on the right-hand side, we're looking at the target or the response, right? And when we look at the prediction, the difference now is that I no longer have a probability, right? If you recall, in classification, we had a column that was the probability, right, of good, or probability of 1, right? And in this case, I only have really the numerical prediction, right? That's the idea with this process. And in terms of data preparation, then, the data preparation is going to be very, very similar to what we did with classification, right? We want to split the data into a test data and a build, right, or training data. Then we want to score that test data. And now I want to compare the model predictions with the actual known responses. But instead of computing the famous confusion matrix, right, that we did with the classification models, in this case, we're going to compute some goodness of fit statistics. We're going to talk about them, and I'm going to show you the code, and it's very, very simple, actually, the things that we can do with that. So for data preparation is, again, the same slide that we saw for the classification. In general, you want to look at missing value. You want to work on standardization and normalization of values. You want to do basic data transformation as well. And it is definitely important. In regression, you will see when I show you what you normally have, especially problems with outliers that might be very complex. So Oracle Machine Learning, as I mentioned before, does include automatic data preparation. So we have these automatic data preparation. We have heuristics that will allow you to do all of these. And in particular for regression, what we're going to do is we're going to do normalization, right? So we're going to normalize all of the numerical values between a range of 0, 1, typically, to make sure that you can work with these different ranges. Now, in terms of the outlier treatment, then, so a value is considered an outlier, of course, and we got to make sure that we work with them. There are outliers that are nominal, and you will have problems when you have those numbers, right, that are too large. There are other outliers that are explainable, so you will be able to remove those outliers, and we're gonna see about that specifically in a minute. Now, one of the things that we can do for the initial process here, right, is regarding the intuition. So say we want to take a look at departure delay and arrival delay, right? So on the bottom, I see a departure delay of a flight, and on my response variable, I have the arrival delay of my flight there. So what might happen, right, is that you can probably think about it, right, more a little bit, with an instinct. If you think about it, there are many times that I've been in enough flights. So there are enough, there are times when there is a departure delay, but the plane can actually catch up, right, during the flight. So if it's a minute or 2 minutes, he can make those minutes, with a faster acceleration, right, a little faster speeds. There are times that you cannot do that, right? So if the delay starts getting into 30 minutes, you're not going to make 30 minutes in the air, right? It's very, very difficult to do that unless the flight is super long and you get some tailwind or something. But in general, that's what you could say. So let's assume, right, this is something like that. So when you look at this, what we're trying to do here with a function or with a predictor, right, is trying to draw a line here that would actually help me identify for every departure delay, what is the expected arrival delay, right? And when we think about it, just for now, if you think about it, what would be the best line, right? What would be the correct line, right, on your mind? So normally, what happens is you could try to draw something, right, with your hands there and say, okay, I think this looks better than the other, but that is your intuition talking, right? So you can see there is correlation, right? You can see there is a line that grows. So to your mind, it makes sense. But to pick the correct one, there is a method called the ordinary least squares, right? So what this method does is basically you actually get the sum of the squared distances between each point to your line, right, to your predictor. And you're trying to minimize that. So that's basically what the ordinary least squares does. It takes that a line, right, and it adjusts that line to be able to minimize the distance between the points and the line, so that now you get a line that is at, the best probably possible, right, straight line that cuts through those points. The idea of the squared here, right, and is because the distance is positive, right, but you also have a negative distance, right? If you're summing up positive and negative distances, they might zero out, right, or they might cancel each other, and you don't have a good adjustment there, right? So then the idea is that you use either a squared distance, or other times you could use things like the absolute value as well. Okay, there are other methods that do that, but this is the most generic method, right, is the least squares, and you're looking at that process. So now, with that in mind, what the regression model, expression is basically when you're looking at your target, right, you have an intercept term, right, and the intercept is here, that beta 0 there. Then you have the attribute coefficient. So for every attribute you have on your model, you have a coefficient assigned to it. And then you have an error component, right? So in this case, what we're looking at in our little simulation here is basically the intercept term for us is 1, which means when the departure, right, is 0, the arrival delay is 1, right? That's our estimate. So I'm saying, I'm departing the flight on time, and I arrive 1 minute later, or 1 minute late, right? Even if I depart on time. That's what our little model is showing here with our data. But also the attribute coefficient, right? If I have a 45-degree angle there, then that guy will be 1, right? So that is very easy to see that that kind of process, because then what happens is when I have 1 minute for 1, you get 2 minutes on the arrival delay, right, and so on and so forth. So you got a basic model del and the error, right? So that again, that's just a very simple, basic visualization of what the models will do, right? But we're going to see them in more detail. So other algorithms used for regression, right? So what we talked about so far was the basic linear regression model. But there are many other methods that include that, right? Support vector machines, neural networks can do regression, and XGBoost can do regression as well on our engine, but that's coming. So it's available today on the beta versions of Oracle 20C, but it's not available yet in the environment in the cloud. So I'm just putting it with an asterisk here. So in terms of evaluation, then, how do we know that a model is good or not, right? So normally there are a few things. So there are a few methods that have goodness of fit, right, of a regression. In the case of the linear regression, typically you look at the coefficient of determination, so the R squared. And the R squared, basically what it tells you is the proportion of the variance in the dependent target variable, right, that is predictable from the independent predictor. So what it's saying is how much of that variation can actually be predicted, right, by your model. So basically, that's what it's saying. Normally, if you include an intercept and you have a simple regression one term, then normally that is really the sample correlation coefficient. When you look at the models with one predictor, again, the R square is looking at the explanatory power of models. So when you have more than one predictor, then the adjusted R square tries to compensate for that, right, and adjust that using the number of predictors that are included in the model. So that's why it's helpful when you're comparing several models with a different number of predictors to look at the adjusted R square. Okay. Again, not all the models come out with those computations out of the box. So normally, what we use to compare models that are more generic, right, are actually looking at the quality of the predictor versus the actuals, right, versus the original. So there are many ways, right, but the basic ones are the mean absolute error. So basically, this guy is looking at the difference between the prediction and the actual, but in an absolute value. Again, you're summing up numbers, right? If you let the numbers be negative and positive, then the sums are going to be just strange. So when you sum up these numbers when they are absolute values, it's easier because then they're going to be on the same scale as well as the target. This number is in the same scale, so if you're looking at minutes in our problem, the scale is going to be very easy to understand. So the mean square error is, again, the same thing, but you're now doing the square differences of the components. Now, because you're squaring the differences, then this number, right, is going to be more sensitive to outliers for sure. But then at the end, you can actually run a square root of that and end up with the variation that is well known and much used, which is the root mean square error, okay, the RMSE. So we're going to see the calculations are very simple, right? As you can see, it's just the sum of the differences between what you're predicting and the actual, right? And so these are very, very easy things that you can compute. With that said, we also have AutoML, right? So I think I talked about AutoML already. And in this case, again, it still makes sense. You are going to have model selection, we're going to have feature selection, and we're going to have auto-tune working for AutoML for regression this time. So we're going to take a look at that into our demo section. So right here, I have then our environment. And basically, I will, as soon as we have the Oracle Machine Learning for Python available, you guys are going to be able to see this demo in the GitHub. So I'll leave that there with all the descriptions on the components and the data. So you'll see the links to the data and where to get it, what is the contents of the data set, and things along those lines, right? Again, same kind of basic initialization of the environment. And I'll, again, take a look at the exploration, right, of data. So I'll sync up my data. So this time I'm using an on-time data set with 10,000 records. So it's a small sample, because I wanted you guys to have a visual, right, when I do my plots and all the models. So we have a small sample here of 10,000 rows. And if you look at the contents, then you can see I have a year, month, day of week, departure time, right? Then you have arrival times, right? You have carrier, flight numbers, elapsed times, and this is what I'm interested in, right? So the arrival delay and departure delay, right? And this guy was going from Las Vegas to, I think this is Orlando. Probably not, because it's too short for Orlando, but anyway, so and whether the flight was canceled or diverted, right? So if you have something very basic, what we can do, right, is we have a function called .describe that, again, we can show very easily a description of the numerical values, right? Numerical variables that are in the data set. So I can see count, mean, maximum, standard deviations, right? So I can see, for example, there are some very weird arrival delays here, right? Departure delays are still reasonable, okay, but I probably in my entire, more than 2 million miles flying, I've never seen a flight leave 26 minutes early, or I would have missed probably, but it's kind of strange, right? It's still kind of very strange, but yeah, flights that are departing 900 minutes late, it's also kind of like an exaggeration, right? But you wouldn't be waiting for more than 10 hours sitting on a gate, but probably maybe those are flights that left the day after, right? Things along those lines. Information about distance. Also, again, it's very rare that you will take a flight to go 21 miles, right? I cannot see that happening unless you go through a helicopter, right? But a plane is going to be very, very strange. But anyway, so you have canceled, right? So you have, as you can see, the average here. So you have 1.5% of the flights have been canceled, and almost 0.2% of the flights were diverted. Right? So those flights never finished, right? So cross correlation then between attributes, you have a function .core that gives you the correlation between these, right? And because today we're going to be looking at arrival delay and departure delay, then this will give us an idea. So I have an 86% correlation. So that means they do have a lot of correlation, right? They do have a lot of, and again, it makes sense, right? If I delay my departure, it makes a lot of sense that my arrival is going to be delayed. Right? So that makes sense right there. So looking at real quick here, I'll cancel and diverted flights. I can see that if the flight was canceled, it was not diverted, so it makes sense. If the flight was diverted, it was not canceled. So all of these things, again, make sense, right, out of my 10,000 flights. So I have a few functions in the Oracle Machine Learning for Python, right, the histogram and the box plot functions that can give me an idea. So I'm looking at the distribution of arrival delay, right, because now that's what I want to predict. And yeah, I can see that these kinds of outliers are kind of insane, right? These numbers are really kind of out of the ordinary, right? So we're going to need to do something. But if we there are other functions that Python can help you with, which are these multiple histograms, right? That you can really quickly have a look and understand what's going on with any data, right? So data with months are kind of like numerically not very stable here, it looks like. Departure times, of course, they make sense, right? There's a time overnight that flights just there's not a lot of flights departing at that time, right, at the time of the night. In terms of the years, different years, concentration on certain years there. But same thing with, you can take a look at that with histogram. Scatter matrix, that's something that I would use to have a quick look at the entire data set. I think it's valuable just because when you're looking at this, you have at least an idea, right, of whether, if a variable is related to the other, you're going to start to see some straight lines here. And if the variable has nothing to do with your target, then you're going to see something that's completely like that, which has nothing, no trends up or down, right? That's something like just straight out, nothing important. So it gives you a quick view of everything. So we're going to use, again, departure and arrival, and we want to plot them, right, one versus the other. So you can plot it with Zeppelin, but you can do the full plot in Python here, for example. And you can see how strange this thing looks, right? So, for example, immediately you can see that this guy looks completely out of the ordinary. So I have a flight that is departing with more than 300 minutes of delay, and it's arriving, more than a 900, almost like 900 minutes early, right? So this is a teleportation kind of thing. You went to the past or something. So this does not make a lot of sense. So probably someone forgot to register the number or something happened. This might be also too much, right? So you can start seeing that, especially because regression has some sensitivity to very large data. This point could actually create the straight line goes to the wrong way easily, right? Because you're going to try to minimize the square distance, right, from this guy when the line is over here. So the line is going to pull up, and then you're going to end up with a line that might not cut off right. So what we're going to do is we're going to remove some outliers. So normally you have to make some assumptions, right? Smart assumptions. You want to be smart about it. But in my case, what I'm saying is, I'm going to look at arrival delays that are less than 60 minutes, departure delays that are less than 60 minutes, and then arrival delays that are more than 30 minutes, early, right? And then departures that are at, 10, at a maximum 10 minutes early, right? I don't think, again, that a flight leaving, more than 10 minutes early makes a lot of sense, unless, of course, the flight is full, everyone is on board, so there's some advantage to just leaving right the gate at that time. But so when we cut off, right, you can now see the difference here, right? So when we do, you go from this, right, which is very strange, it's got some crazy numbers out there, to something more manageable and understandable, right? So now you can see that trend. So there are still a few things that are strange here, right? So you can't cure everything. So you have a flight here leaving, with almost 30 minutes of delay, and it arrived more than 15 minutes early, right? So again, these are all types of things that if you have time, you would probably want to investigate this specific flights. You would probably might want to check what was the distance, right, of the flight. Did the flight have time to actually do this, right? Because otherwise that might not make sense, right? Like this guy is getting 50 minutes of delay to depart, and it only arrived 50, less than 20 minutes late. So again, this guy got, made up 30 minutes on the flight. It's a lot. I can tell you it's a lot. Flying across the country, especially, right, where you don't have, too many hours, right, of flight, making up 30 minutes of a delay, it's a lot. So again, it's worth, investigating more and diving deeper into this thing, because the other case, right, when you don't have a departure delay, but you are arriving 30 minutes delayed, right, 60 minutes of delay, that is more normal, right? Because there might be a storm, right, in your destination. The plane has to be, going around and around, or there's a busy airport where you can't find a spot. So there are many things that can go wrong there. Arriving, with a larger delay still makes sense, right? So let's go to our analysis then. Basically, the first thing we do, right, remember, was splitting the data, right? So we're going to split the data. We're going to do a dot split on our new clean data, right? Remember that this new clean data is actually an automatic query, right? Behind the scenes, there's no data assigned to it. It's just a query on top of the original data set. And now we're creating a view to use the split here. We're splitting 70-30, right, between training and test. And then we can check both, right, both data sets. So I just want to make sure that the two data sets look reasonably similar, right, so that we are evaluating, we're building a model here, and we're going to evaluate it over here on something that is similar, right, in terms of distributions, right, of the departure and arrival. So to build a model, we're going to create a goodness of fit empty pandas data frame, right, because I want to accumulate each model name and then the quality of each model. And then we're going to do linear regression. So we're going to do a GLM regression. I am just doing that by training data set Y fit on X. I will predict, I run the prediction, and in this case, I'm asking for the interval of confidence, right, to be also predicted together with the prediction at a 95% confidence level. So what I see now in my output is I see my arrival delay, I see the departure delay here, and I see my prediction for the arrival delay, right? This is what is trying to predict this guy. And I see the lower and upper confidence bounds as well for that prediction, okay? So when I look at the model itself, then the model itself basically is going to give me some information about the model. So it's going to say, what is the confidence level that I asked? So those are some of the settings, the basic setting it did and it used. So it's got the automatic data preparation. If you recall, we were talking about it. And then it's saying, okay, this is the model that it used to use the ridge regression. These are the global statistics, so adjusted R-squared, like we talked about. Then it's got an R-squared. Then it's got an Akaike information criterion. So you see all of that information by my model and what was the attribute it used, right? So I'm only using one attribute, right? As again, we were using only one guy, right? Departure delay this time, and the coefficient. So I get an intercept of minus 1.6, and my departure delay, which the estimate is 0.96. So that's basically the formula, right, that we had. The intercept is my beta 0, and my beta 1 is 0.96. So to have a visualization of what that looks like, I am plotting here the arrival delay, departure delay, and the regression line, right? This is what our model thought that it would be the best representation of trying to predict the arrival delay. And remember, again, that I mentioned, right, this guy's going to take into account all of the original points, right? But in this case, I'm looking at the predictions. Remember that I built this model on top of the training data. So there might be things here that the model did not take into account. For example, some of the outliers down here. Right? Otherwise, if I was building the model with this guy so far, maybe this line will go, come down a little bit, right? So this is, again, looking at the predictions that I had using my training data. I'm like testing this guy. So I'm going to test it now, and I'm going to look at some of the things that normally we do, right? When we're trying to predict, we're using arrival delay versus the predicted. When you do when you do actual versus predicted, you normally would expect, if the model is perfect, a 45-degree line, right? Because I am saying, actual is 0, the prediction will be 0. If I predict 20, I expect the prediction to be 20. If I say the actual is 40, I would predict 40, right? So if I had a perfect model, I would have a 45-degree line represented over here. This is not the case, right? You can clearly see that there are very much missed predictions, especially on this side here, right, on the larger arrival delays. So another graph that normally we use is showing the residuals. So when we present the same chart, but this time I want to see at my predicted versus the residuals, right? And you start seeing this kind of thing where you're seeing that for my predictions that were between minus 10 and 10 minutes, there is a huge, right? The residuals are big, right? So my model was really not being able to capture all of these things that were happening at this point, versus when I was predicting an arrival delay of 50, my residuals were probably much less, right? So on the 102 class, we're going to see a little more about these diagnostics and the problems and how to try to solve some of these things that you can find on these data sets, right? But for now, we're going to continue with trying to compute then the goodness of fit statistics, right? And remember, we were talking about basically the mean average error, right, which was the absolute value of my arrival delay, which is the actuals, minus my prediction, right? And then I'll sum that, right? So that's the sum of that divided by the count, right? That's as simple as that. You have the mean squared error, which is the arrival delay minus prediction to the square, right? Sum those squares and then divide them by the count. And finally, the same entire thing with a square root, right, on top. So I take the square root of the entire process. That's my root mean squared error. So these three statistics, what this little function is going to do then is just compute those guys based on the prediction data set that's coming in. Because I'm using the transparency functions, right? So it scales. So this can scale to millions of records. I don't have any problem working on that. And I'm printing out the statistics and I'm returning the statistics for these guys. Now, on the goodness of its statistics and for linear regression model, again, I run my function for the linear regression and I store it right in the goodness of fit because I want to see the statistics later on. So I can see that the mean absolute error, right? And then I can see the mean squared error and then the root mean square error, right? So those numbers do not need to make sense for you on one single model. They can give you an idea, but these numbers will be more effective and interesting when you compare models, right? So right now, if I look at another model, I'm trying to do, cubic and square terms. It might not make sense because it's really pretty much of a straight line, but I will try to run a feature selection and a feature generation on my algorithm. So when I try to do that, again, I'll get my confidence levels, my interval confidence. I can increase the confidence there if I want to, 99%. But basically, what I get out in the output here is if the model thought that it was useful, it will add more variables. Otherwise, it will not. So in this case, it didn't think it was any useful to add the cubic or the squared by the departure delay multiplied by itself, right? So in any case, you can see here the basic statistics, right? And then what you got to remember that these statistics that the model are telling you here are based on just seeing the training data, right? So normally these statistics and all these values are going to be a little more optimistic, right, than the actual value. So when you want to see the actual process, right, what you actually see there is then when you try to run it over here, and we can see what it was trying to do. So again, we were plotting the model, right, which actually ended up being the same as the previous, right? We couldn't generate any new features, so the statistics are going to be the same here in this case. Now we switch to support vector machine, and in the support vector machines, again, same thing, right? We have SVM regression. I'm going to start with the linear kernel, right? And in this case, we got our prediction. We have the information about the model out here. Usually that's only really telling you, whether it converged or not, right? But it's not going to tell you a lot more in details on the algorithm, on the model. But basically, this is the output. So you can see it's probably very similar, right, to the regression line at this point, just because, again, this is so linear, right, anyway. So it's very similar to that. What we do the same thing again here, right? We take the prediction output of the linear model and we run it, the evaluation. So you can see that a similar mean absolute error, and then the mean squared error is a little or more than the other one. I think the other one was 120. Another option, when you have more complex features, you can actually get the Gaussian kernel, right? And it's going to give you a little more capabilities on actually creating curves, right? And getting curves into that model. But it doesn't seem that it needs. So when you look at the results again, even the Gaussian kernel is showing pretty much of a straight line here, because again, it's not going to benefit too much from trying to add curves into this, right? So we compute again the same statistics. They are very similar to the linear kernel, right? Now you can mess things up in a way, because you can then decide to start playing with complexity factor, right? So if I added myself some complexity factor to this to play with the numbers and see, can I do something different? Then what happens is, by manually adding a complexity factor, you can start seeing a little different things. Not necessarily good in this case, right? Because again, it's pretty much a straight line prediction. But if you look at what happens, I think you guys can see that the difference, right? So now, because I added that complexity factor, I forcefully asked it to try to create more curves than needed, right? So you can see that trend. That the trend could have been a real thing here, right? Because the data was originally showing something like that, but maybe it's not translating that well when you look at the test data, right? Because the original data might have had some tails that maybe did not translate well. So the original Gaussian was good. The analyses and the defaults were probably better than what I'm doing here, and that can show you that difference, right? And in this case, it actually helped a little bit, just because on the top end you have some sort of a difference here, right? And then on the beginning here, it helped, this little curve helped perhaps take care of all of these outliers over here. But in any case, those are things that you can play with. Neural networks is the same thing. So we can start with a 1-layer 4-node neural network, and that's going to give me, again, a basic output. Normally you get all the topology, you get all the layers and the weights for all the different layers. And then, but because the output is kind of straight, you get almost like in a straight line. There might be a little slight curve in some of these places here, but you're still getting pretty much almost like a straight line, right? And then you get the test, and they're actually showing good. So the fit is very, it's getting very interesting there. A 2-layer now with 4 and 2 nodes, and then I got my activations of log sigmoid functions here. So you can start again playing with that, with that structure, and then you can see there is a little bend right on the top end here. There's a little bend out of that. Let's see if that helped us a little bit. It doesn't seem to help much. And then you can continue adding layers, but in this case, because we're only using one variable, remember, right? Then your network is going to get more complex. You're going to get much more complex structure. You're going to get a lot of coefficients that you need to take care of here. But again, the design is very, very similar, right? So you're not improving too much. So again, goodness of fit of that neural network, I think is a little worse than the previous one that I had. So at the end of the day, you can have, because I accumulated these guys, right, and I was appending every model to this goodness of fit list, you can get a list of that. So you can see, how are the models working, right, and what are the best models listed in here so far. And then, as I mentioned before, we have AutoML. So AutoML, for AutoML regression, then, what we're going to do is we're going to say, please take a look at all of the algorithms that are available in Oracle Machine Learning, and using regression, tell me what's the best algorithm, and you can pass a score metric. So I am actually going to ask for the mean squared error, right? And there's a negative, but that's part of the formula. But the mean squared error, that's the statistics that I'm interested in. You have R squared, you have a lot of other statistics that you can find in documentation that you can ask. And I would like to, show me the 4 top models that you find. And this is my training, right? My X and my Y. So it actually showed me the GLM Ridge as one of the best models, but you can see the difference is not big, right? In terms of the numbers here, we're all the way to like 6 digits, and I think we're still equal, right, on the other side. So it's showing me GLM Ridge as a preference, GLM, neural networks, and SVM linear, right, as the 4th one. So I said, okay, I would like to do some feature selection. Now remember, feature selection, it doesn't make sense here because I have only one predictor, right? So all I'm doing here is I actually commented this out because we're going to be using that for the 102 class. But now I'm only just showing you that, yes, the model does a reduction, it does an analysis on GLM Ridge, but of course it says, you know what, yeah, keep using what you have, because if you don't have any variables, you would only have an intercept, which is a straight line, in a horizontal straight line, which would make no sense, right? So it says, yes, it's smart to keep using that variable. So now I'm going to add then a tuning. So I'm going to take that GLM Ridge and I'm going to say, okay, I would like to tune that for regression. So please tune that model for me. So find what are the best settings that that model should have. So I'm running that. It's going to run the ridge regression. Is going to get the best ridge value possible. It's going to find whatever the solver that helps. It's going to identify all of these settings for me, right? The things that I've not chosen. And finally, then we scored the final model, right? So we scored the tuned model, and we plot it here as well, right? So again, very similar to the other ones. And now we're going to do the statistics, the quality of that model, and finally, I add the AutoML to the other models that I have. And it turns out that AutoML is one of the top ones, right? Because I see it's actually very much the top one, right? Together with the neural networks that I did some customizations, but it's basically in the same ballpark here of the top ones, right? So that was what I wanted to show you guys in terms of the script. Back to the slides. So as always, for more information, oracle.com/machine-learning. But I think we can open up for Q&A.
Marcos, we have a few questions that are in the Q&A listing. One question is, can you tell more about how the confidence interval is computed or used?
Right. So the interval of confidence, you can compute that for the predictions, right? Which then is going to help you understand, a ballpark, or saying, 95% of the time that you do these experiment, you expect that's where it's going to fall. The other types of confidence intervals that you can do is actually confidence intervals on the coefficients themselves. That's also something that you do normally for these regression models. I can probably show part of that on the next class. I'll remind myself to show that with more details.
Okay. Another one is, do we need to separately calculate RMSE and MAE, or querying the model views is sufficient?
For Oracle Machine Learning, you can query the models themselves, and they will have MAE, MSE, and RMSE, but those were calculated on the training data, right, when the model was built. So when you are comparing against test data, that'll be different. You need the predictors, right? You need the predictions to be able to compare them with the actuals. If you have, if you score them, right? If you score the models then you can compute that. If you want to do that per record that you do, if you have the actual and you're just scoring one record at a time and you want to try to compute that, it might not make too much sense, but you can. But normally this is done for the prediction of the test set, right? So that you can actually try to compare the model quality between models as well, right? So by itself and as an isolated number, it might not help too much. It helps to understand the quality of that model, but it's very useful when you're comparing different regression models, right?
Okay. Another one is, what do fractional, canceled, and diverted values mean? I think this was when you were showing some of the visualizations on that. What do fractional?
Oh, right. So the canceled and diversion, you get the fractions just because actually is the average, right? So you have a lot of ones and a lot of zeros, and when you compute on a statistic, so when you want to know what's the average canceled flights that I have, then it basically is the average between all of those zeros and all of those ones. So when it's at 0.01, right, that means 1%. So it means 1% of my flights had cancellations, and 99% of the flights did not have, so they were zeros. So it's easy when you have a variable that is just 0 and 1 to look at the average so that you can have that proportion of canceled flights. Same thing with diversions.
Okay. This was recently submitted. Can you access data on OCI object storage from this interface, or can it give instructions only to the DB and database kernel?
Good question. For now, we would work with the database. That's the current intention. Using the autonomous database, you could easily get access to the object storage, though. But on the other hand, when the solution launches as an on-premise version, then you could have, say, your own environment, right, where you could easily create an OCI connection from that Python session and do these kinds of things.
On autonomous database, Marcus, what about Cloud SQL?
Right, so that's part of the things that Cloud SQL is going to bring as well. So the Cloud SQL capabilities is going to bring that capability of accessing object storage by mapping those as external tables, right, to the autonomous. And then you would be able to query that data directly.
Okay. What data types other than tables can we access?
If we have database tables, you can have database views, you can have these kinds of, I guess that's the question, right? Is what kind of other things?
I think it largely just between the tables and views, and right, external tables, anything that you can map to a table or view should be accessible, like DB link data as well.
Right, and they become available to you as a pandas data frame, right, for you to play with. So the commands that you use on top of those are going to be, your typical pandas data frame commands are going to work on these as if they were local pandas data frames for sure. But you're also able to pull the data through the wire and then use any function in Python as well, right? So you can have local pandas data frames from that data at that point, and then you can play with and do the plots that I was doing, for example.
Yep. There are a couple of questions related to OML for Pi release. I'll just briefly speak to those. So as far as a release date, how soon will it be GA? I mean, it's coming soon. That's what we've been saying for quite some time. We are looking for, certainly this calendar year, but I can't be more specific than that. And is AutoML available on-prem? AutoML is a capability of OML for Pi. And so when OML for Pi is made available on-premise, that functionality would be there as well. It does not have to be an engineered system that this is run on. It's associated with the Oracle database in that case. And let's see, I think we have one other one here. You chose Model A and asked it to auto-tune for many hyperparameters, and finally got some results with RMSE. It is possible that another Model B with hyperparameters HPX can do better than the auto-tuned Model A. Is that correct?
Right. I think it's in my particular case, in my specific case, it could be just because the models ended up being very similar, as I shown in the model selection originally. GLM Ridge and GLM and even SVM were very similar, or neural networks, right? They were very similar in nature. So potentially you could have something similar. I don't think you can have a better, but yeah, that might be a possibility, right? So you can say, well, let's torture a neural networks enough and see whether I can get a better model. So it is potentially true. What I've done before and what I'm going to do next on our next class is actually to let the AutoML run the top 3 models, right? Because I think that makes sense. And then you can at least have your actually best models, completely well tuned. So now you can probably compare in a more fair share there, right? So this what I did now was kind of simple, right, and short and a quick thing.
Okay, and we have a couple of other questions. Did the routines leverage partitions? What were the source table? Were the source table partitioned? There was no explicit mention that the person saw in the routine.
Right. So there is no partition in this case. You can, if you had a partition, right, and then at that point, the idea is you could have partition models. So for example, we could easily say, you know what, instead of building a regression for everything, I think that every airport is different, right? My feeling is that, Chicago, right, is always complicated in the winter, right? The airport is always like a 50-50 if you're going to get stranded there, versus down here in Miami where, things are always normal unless you have a hurricane, and at that point it's complicated as well. So you might want to say, you know what, let me try to run one model per airport of origin. So if you do that kind of thing, you could easily partition the data for that and run a partition model. If you run a partition model, the Oracle Machine Learning does it for you. You only have to say, please partition by origin. And you get all of these algorithms running in the background in parallel, right? As much parallelism as are available to you, right? At that point, with your database, with your CPUs that you have available, you're going to be able to run all of those guys in parallel. Yeah.
Okay. When do we need to do scaling? Is it always good to do scaling, and what are the best practices?
Yes, I think that's probably a best practice for sure. I think it's always important to do scaling, especially when you have variables that have different scales, right? So in my case, departure delay, arrival delay was kind of okay, but you're going to see on the next session when I start introducing other things, right? Elapsed time, distance. So you start getting things that are thousands to things that are seconds, right? To things that are, other scales. Then it's normally better for you to auto-scale everything and put everything in 0, 1. Otherwise, the regression methods, because they use the variability, right, of the variable, of the attributes, they are going to prefer, right, attributes that have the most variability that can help me. And the problem is, what's the best variability? Well, the one with the most variability, the one with the biggest number, right? So then if I am looking at something like age, that's never going to be picked, right? Because that's a number between 0 and 99. When I have something like, the seconds or minutes that go to thousands. So the variability is much larger, and I'm going to prefer that to try to help me explain my phenomenon. So many times, and because Oracle Machine Learning does it automatically for you, so I did not have to do it myself by hand, but that's something that I can include on the next class as well.
On what basis do you select SVM linear and Gaussian? Is it to fit the regression line most of the data points?
Right. I think that normally the linear would is normally helpful because it's simple. So SVM linear is a simpler model, right? The last time we talked about the classification algorithms, we were showing that with the Gaussian, we can actually create very, very complex algorithms. But the problem is those can actually be over-tuned, right? So you can end up having an algorithm that when you try to apply now to the real life, it's so over-tuned that you're not going to get a good response, right? A good result on the test set. So if you can get away with a simpler model, the simpler model wins, right? Every time you have to measure two things, the simpler model is always the better, right? If the quality of the model is the same, I would never pick a neural network, for example, right? If I can get away with something simple, it's always better to try something simple and more stable than something too complex that can go crazy when you get just a little twist or a little change, right, in what happens. So that's my 2 cents on that.
There's also you might also ask about the transparency of the model. That how do you want to understand what's going on? At least for the SVM Gaussian, we don't provide model coefficients, and so if you want to understand what the coefficients of that model are, then you'd want to go with a linear model. So it also depends on what are the patterns, or what are the patterns in the data, and whether or not they're linearly separable. So you might want to try both and see what you get.
Mm-hmm. Yeah, perfect.
All right. And how often would you retune the model in this example? Was there anything in this data set that gave you basis to decide that?
Normally what happens is actually more towards the problem that you're trying to solve than the modeling tool that you're using, for example, right? So if I'm thinking about flights, right, then once I finish working on something like my flights, then I would probably try to look at the model again, every month maybe, right, and evaluate the model every week, but then maybe try to look at the model every month or every 3 months, because you have the seasonality, right? So you have the quarters, the end of quarters, the children go on vacations, right? So all of those things might affect your problem, right? And my problem, what I was looking was arrival, flights delays, right? If what you're looking is a defect of a machine, I had a case where a customer was looking at a machine, a gigantic transformer that would only fail every 20 years. So the time to when the problem is going to happen, right, or the time to where trying to understand your phenomenon is the most important thing. That's going to give you that precise information.
Okay. Great. And there was only one other question left here. In your graphic of fitting the line on a set of points, you talk about minimizing the distance of the point from the line, but the graphic highlights that it's the y-axis distance only that's provided. He wonders, why wouldn't you show the distance as a perpendicular line to the regression line?
Right, because it's not really a projection, right? You're trying to see for that specific arrival delay. So I had a 2. My departure delay was 2. So I'm trying to check for that point what was my prediction versus the actual. So that's a vertical line, right, between those 2 points that I have to check. So it is not like a normal projection where you would actually project it perpendicularly to the line, right, and try to see the distance over there. It's a little different.
Indeed. All right, well, that's the end of our questions. And thank you very much, Marcos, for a very exciting and interesting session on regression. And we'll get to everybody next time, where we go into Regression 102.
Excellent. And the last question, I think, is I just see the model object, right? That yes, the model object can be saved and stored in the inside the Oracle database. It's a special object, so we can also show the way to store our data store, right, in the AutoML for Py on the next session. Okay.
Great. All right. Take care, everyone.
All
Until
right.
next time.
Thank you very much. We appreciate it.